what happened? Okay. Anyway, so let's get started. First, about one notification. Next week, because I'm going to attend the international conference, so next week's lecture will be canceled, and all lectures will be postponed 1 week later, based on the scheduled dates. So anyway, the labs will still be as normal, so you still need to come to the lab to do something for Spark. This week's lab is still for MapReduce. And from next week, because now we are going to learn a new topic about Spark, so the lab will also be about Spark, not about MapReduce anymore. And I hope that you can finish all the labs on MapReduce, because from today we'll move to a new topic. Okay. Also next week, the third assignment will be released. So what is the deadline for the second project? Okay, I give you 3 weeks. Okay, I will make a decision later to see if the third project will be released next week or the week after next week. And the marks for the first project will be released by this weekend. So you will be able to check your marks maybe next Monday. But because next week I'm not here, so maybe if you have any questions, you can first contact the tutor and the course admin, and then if they cannot solve the problem, then after I'm back, I'll help you to update your marks if there's any problem. Okay, so let's get started about today's lecture. We will have 2 lectures on Spark. Actually, I hope that I could have more lectures on Spark. But because of the time limit, we are not able to have 1 more lecture on Spark. So, but I have to say, Spark is more widely used than MapReduce nowadays. So I think if you are interested in big data relevant jobs, you should concentrate more on Spark rather than MapReduce. I believe Spark has much more bright future. So let's first look at the motivation of Spark, why we need a new platform, although we already have MapReduce. For MapReduce, based on what you have learned, we have a map function and reduce function, right? And so the major problem is that to divide your task to subtasks. And these subtasks first be assigned to the mapper tasks. And the mapper tasks will generate some intermediate results. And these intermediate results will be aggregated by the reduced tasks to generate the final output. So this is a basic data flow of the MapReduce. It greatly simplified the big data analysis on large and reliable clusters. And it is great at one-pass computation, but not very good at multiple round computations, such as the second project. So actually, from the second project, you should be able to know that a lot of iterations or a lot of round of computations not quite useful, because they only update a few vertices in the current round, right? But still, you need to do the same thing in every iteration. So there's some kind of a drawbacks of MapReduce. Actually, the users in both industrial and research, they have some more observations based on the big data analytic problems. And in different application scenarios, the users may want different features of the platform. For example, for some more complex or multipass analytics problems, such as machine learning, one of the most widely used example is the k-means clustering algorithm. And also for many graph algorithms, such as the shortest path problem. For shortest path, and in Lecture 5, we have learned that you need to use multiple rounds of MapReduce jobs to get the shortest path. And this is the first type of problem that MapReduce is not quite suitable, actually. And another type of problem is called interactive ad hoc queries. So like in database, in traditional relational database, and you are able to use SQL language to interact with the database, right? So you are able to submit a query to the system, and the system will return some results to you. And most of the time, actually, the result will be returned to you in a very short time period. But for MapReduce, MapReduce is able to deal with such ad hoc queries. And the third type of problems is real-time stream data processing. MapReduce is mainly designed for batch job processing. So your data is already there, and you just throw you design your algorithm. And based on your algorithm design, so MapReduce will follow the logics, follow the data flow to process the data. And then the results, so the structure you know, MapReduce will read the record from your data set one by one, right? And then it will scan the data set from the beginning to the end, and then the final output will be generated based on your MapReduce programs. But for real-time processing, it's obvious. Oh, sorry. Okay, so for real-time processing, for streaming data, and the data is not static. So it means that you are not just given the data set, then you process this data set. Actually, the data set is dynamic. It keeps evolving. And one example such as Twitter, right? In Twitter, every day we as users, so we will post tweets to Twitter, and the system keeps receiving a lot of messages, a lot of tweets. And so it means that you cannot just put your data there. You need to update the data on the disk. And then based on the streaming data, a lot of tasks requires real-time processing. It means that you need to get some kind of results almost in real time instantly. So MapReduce, as you know, the MapReduce need to first read data from the beginning to the end, and then it's from disk to memory and process by the mapper task to do some kind of processing and generate some intermediate results. So the intermediate results will be stored on local disks, and then the reduce task will get the data through HTTP. So there's some cost on network. And then finally, the final output will be stored to HDFS again. So you can see that the whole procedure actually costs a lot of time. And for real-time processing, obviously, MapReduce is not very suitable. So to deal with these type of problems, actually we need some new processing platform rather than MapReduce. So this kind of problems need faster data sharing across parallel jobs. And so in order to deal with different type of problems, actually we have some different systems. For example, for Prego, we have learned for graph processing in lecture 5. So we still use a shortest path problem as an example. So you can see that Prego has a very different objective. So for MapReduce, the basic operations are MapReduce, but for Prego, it's designed for graph data. So it's a vertex-centric. So it thinks from the perspective of the vertex from a vertex. You need to define a behavior on the vertex. And then so the vertex will receive some messages, and then based on the messages it receives, so according to the behavior you have defined, it will do some kind of operations, and then send the messages out and then to the other vertices. So that's a basic idea of Prego. It's mainly for graph processing. So you can only model your data as a graph, and then you define behaviors for the vertex in your graph. So that's for Prego. And Storm is a system for streaming data processing. And So this type of platforms are specialized for these for different problems. And so the major problem MapReduce is that it's kind of although it's designed as a general programming model, but it's only suitable for the one-pass computation on large data set. Just one round map and reduce. So that's very, its performance will be very good. So okay, it's okay to have several rounds of map reduce, but not for iterative jobs such as graph-based algorithms in the shortest path problem. And also it is very hard to compose and nest multiple operations. You need to first get one round map and reduce and get some data and stored in HDFS. And next round, your map task need to read the data from HDFS again. Okay, it's not very easy to nest multiple operations. And also there's no means to expressing iterative operations. So what you can do is that you need to control the iterations in the main function. So I give you the template, right? So you see the template. So that's what you can do. In the template, in the main function, you need to control the iterations on your own. So there's no other means you can express iterative operations. And as implemented in Hadoop, so all the data sets are read from disk. So the data flow is that your map task will read data from HDFS. And also, finally, the reduced tasks will write your data to HDFS as well. And all the data is triple replicated for reliability. And this is briefly mentioned when we learn MapReduce. So it's used to deal with the disk failures. So each chunk of data will be duplicated for at least 3 times. And it's not easy to write MapReduce program using Java. So by so far, all the labs are based on MapReduce, also based on Java. We are using Java to write MapReduce jobs. So you can feel that actually it's not very convenient to write MapReduce programs. So the benefits of data flow is that the runtime can decide where to run tasks and can automatically recover from failures. So that's advantages of MapReduce. But the major problem is that it's very slow because of data sharing mechanism in MapReduce, because data sharing is based on disks. Okay. For example, for the iterative jobs, such as shortest path, you read some data from HDFS and you write some results to HDFS again. And that's for the first iteration. And in the next round, you need to read the data from HDFS again and then do the same thing, write the result to HDFS. So you need to repeat this procedure again. So you know that actually reading data from disk to memory is a very high cost. So if there are many rounds of iterations, it means that you have a lot of cost wasted on reading the data, wasting on the I/O cost. And another type is for the ad hoc queries. So for each query, so you can use MapReduce to solve such kind of problems, such as a query. So you're given data, you can do some kind of search based on data set. You just need to write your MapReduce jobs. But the problem is that for the same query, if you only vary the parameters of this query, you don't change any other things in the query, just parameters. You still need to read the data again from HDFS to the memory in your cluster for the processing, and then write the result to HDFS. So you can see for the complex applications, the streaming data processing and also interactive queries processing, they all need one thing that MapReduce does not have. That is the efficient primitives for data sharing. For data sharing, MapReduce is based on disk. You read data from HDFS, you also write data to HDFS. So HDFS is the only way that you can share the data across different rounds of iterations or across different types of jobs, such as for different queries and for different rounds of iterations. And this is one example to show that how the data sharing is achieved in MapReduce. For example, this you can think of this graph problem, And in the first round, in this stage, your MapReduce jobs will read some data, and then after the processing, the data will be written back to HDFS to disk. And in the next round, the same thing happens again, again, again. So disk I/O is very slow. So if you can see that you also need to exchange data across different different computers. So the network cost and also the disk cost are very high in this kind of algorithms. And for interactive queries and online processing, it also involves lots of disk I/O because for each query or for each job, you need to read the data again for each query, for each job. So because all the data is shared across disk, it's not in memory. And in PageRank, so that's an example of the PageRank. And in PageRank, you need to repeatedly multiply the sparse matrix and the vector to obtain a new vector. Also, this requires repeatedly hashing together the page, adjacency list, and rank vector. So for different iterations, this is for the graph structure, and this will not be changed. But in each iteration, you need to read the graph structure from HDFS. And also, you need to get some results from different nodes. And the same file, actually, they are sent from this iteration to the next iteration again, again, and again. So that's what you did in your second project. Actually, this is not very efficient to solve the graph problems, right? So what we have used now for the hardware we have used is we have used lots of hard drives. That's where HDFS is designed for. HDFS is designed across a large number of hard drives. And also we have a lot of CPUs. So MapReduce use these CPUs to do the map and reduce tasks. But remember that actually we also have a lot of memories. So that's a major motivation of Spark. So Spark also utilize memory to do the big data analytics. So because the data processing in memory is much, much more efficient than reading data from disk to memory, then process it, right? So that's a major observation and also the major motivation of the Spark project. And the goals of Spark is to keep more data in memory to improve the performance. So if all the data can be kept in memory, well, your data processing will just be based on memory, and there's no cost on I/O, on disk I/O, right? So just because of this, you can save a lot of time. Just because of disk I/O, you get rid of the disk I/Os. And it extends the MapReduce model to better support two common classes of analytics applications, the iterative algorithms for machine learning, such as k-means, and also for graph algorithms, such as PageRank or shortest path, and also for interactive data mining. And so this is kind of, you can think of this as a query, and you submit query to the system, and it will return some results to you. The kind of interactive way to do the data analytics. And it also has an enhanced programmability. It integrates into Scala programming languages. It also has Java support. You can also use Java to write Spark program, but you can use Scala to more efficiently write your program, as you can see in the next week's lab. And also allow interactive use from Scala interpreter. So you have a Spark shell, and in the shell, so you can just write some comment to process the data, and Spark will give you some instant feedback. So we can see the difference between Spark and MapReduce in this figure. So data sharing in Spark now is based on memory, and we will learn a data type called RDD, called resilient data structure. And this RDD is held in memory. So now for different iterations, all the data, so you only need to read data from disk once, just once, from disk to memory, and then data will be kept in memory. And you do something to the data, and the data, the results will be written to memory, not disk. And for the next round, okay, the next round just need to read that from memory instead of from the from disk. And then you do this again and again. So you can see the difference here is that the major difference is that you do not need to write the partial results to disk anymore. You just need to use the memory to hold the data for the next round of iteration. And also for the auto queries, and you also need to just read the data once from disk to memory. And next, for different queries, you just need to process the query according to the data already in memory instead of fetching the data from disk again. So this also increases efficiency. And according to some results, so Spark, for the same problem, for the same data set, Spark is about 10 to 100 times faster than MapReduce using network and disk. Let me see the figure. Here, so you see MapReduce uses disks for data sharing and also for the interactive queries. But for Spark, we use memory for data sharing. So that's a major difference. And what is Spark? It's kind of the most popular answer to what is beyond MapReduce. And it is also an open source project. It's for large-scale data processing and support generalized data flows, not just MapReduce. MapReduce is also supported by Spark, but it has more functions for you to use. So more generalized data flows can be supported in Spark. And it is written in Scala and with bindings in Java and Python as well. So the most popular way of using Spark is anyway, the Scala. So that's why we need to learn Scala in this course and also do some labs and also do the projects using Scala. Anyway, if you like, you can also use Java and Python to write Spark programs. That's also supported. It's first developed at UC Berkeley in the MP lab in 2009. I think this lab is the best lab on database. They have developed many useful projects. It's open source in 2010, and then now it is already get some commercial support from this company called Databricks, and it's just a brief history. The current version is 2.3.0, and so in the lab you are also going to install this version for Spark programming. It's a fast and expressive cluster computing system interoperable with Apache Hadoop. So actually Spark and Hadoop MapReduce are two different systems. But anyway, you can still use Spark and Hadoop together. But it's mainly Spark will just use HDFS. Use HDFS for the data storage. So first you need to read the data from disk to memory, right? So you can use HDFS to hold data. So that's it. That's a major connection between Spark and MapReduce. And it improves efficiency through in-memory computing primitives. So all the computation is based on in-memory operations, not based on the disk operations. So in MapReduce, in the map task, in the map of functions, you will read data from disk to memory. But in Spark, normally you just need to do operations based on the data already in memory. And also it supports general computation graphs. And this is also different from MapReduce. So in MapReduce, they just map, and the reduced tasks need to wait for the finish of all the map tasks, and then the reduced task can begin. But in Spark, it is not like this. You have more generalized computation model. And also it improves usability through rich APIs in Scala, Java, and Python. And you also have an interactive shell to do the interactive data analytics. And remember that Spark is not a modified version of Hadoop. It's totally different from Hadoop MapReduce. Okay, it's not just extension of Hadoop. And well, the motivation is because Hadoop MapReduce use disk for data sharing, and then Spark use memory. But it's not just a modified version of Hadoop. That's quite different. And also, it does not depend on Hadoop because it has its own cluster management. So for the resource management, for class management, Spark also has its own manager, not based on Hadoop. But it can use Hadoop Yarn to do the cluster management. And for Yarn and HDFS, we will briefly give an introduction in some lecture in week 11 or 10. So by now, you just need to know some basic ideas of them. And Spark uses Hadoop for storage purpose only as a site. Mainly, it uses HDFS to store the data. And then, so initially for your Spark program, you need to read the data from HDFS. So that's it, that's all. And then next, for all the subsequent operations are based on the in-memory operators. And all this has already mentioned before, so it's about 100 times faster than MapReduce. But although even all the data is on disk, Hadoop Spark is still about 10 times faster than MapReduce. And just because it has a more generalized computation model instead of just map and reduce. So that's a big improvement comparing Spark and MapReduce. And for the coding, actually you have about 5 times less code. In MapReduce for Java programming, you write a lot of classes and a lot of configurations. But in Spark, by using Scala, you don't need to write so many codes. And it's very you can see it from the labs. It's very efficient for programming. In Spark, there are 4 major components. Spark SQL, this should not be Shark. Shark is the earliest version of this component. Now it's not called Shark anymore. It's called Spark SQL, SQL on Spark. And second is called Spark Streaming. It's used for real-time processing. And Spark SQL, according to the name, you should know that this is used to process structured data. So if the data is structured, such as big tables, then you can use Spark SQL to do the processing. And actually, in this component, you can write SQL statements to do the queries and to do a lot of tasks. So these are supported by this component. And Spark Streaming is used for streaming data processing. And when your data is not static, it's dynamic, it's streaming data. And you can use Spark Streaming to do some analytics jobs. The third part is called GraphX. And this is actually based on, partly based on a Prego model. And it's used for graph processing. And we will learn GraphX in the next lecture. So there you will see the difference between MapReduce and Spark GraphX on graph data processing. We will again use the shortest path problem as an example to learn GraphX. And the last one is called MLlib as a machine learning library. So this is used to support the machine learning algorithms such as clustering, classification, recommendation, regression, and many popular machine learning algorithms are already supported in Spark. So if you are interested, you can read the documents of this component. You can see how many algorithms are already supported by Spark. And actually, you can also use these some functions supported in MLlib to design your own machine learning algorithms. So we will just briefly touch this part. This is not a focus of this course. Okay, so that's about Spark. What you need to remember is that, okay, Spark is it utilizes memory for data sharing, okay, and it has it support more generalized computation models, and it has 4 main components: the Spark SQL, Spark Streaming, GraphX, and MLlib. So each component is suitable for different type of applications. And they are all based on the Spark core. So this lecture will mainly learn the Spark core, learn this part. For data sources, so where the data you can read from in Spark. So one source is HDFS at the site, so that's where Hadoop can be used in Spark. Your data can be stored in HDFS, and then in Spark, so first the program can specify the data locations and then read the data from disk to memory just one time. And you can also store your data in local file systems. So then, for example, in your local file system, you just need to specify the URI of your file, and then Spark can read the file from your local disk to memory. And S3 is a file structure supported in file system in Amazon. You can also use S3 to store your files and then read the data from S3. And also HBase or Cassandra, these systems are also supported, can also be used to store the data in Spark. So Spark can also read data from these systems. So this is a brief view of Spark. So this is Spark core, the core component. And then upon Spark core, we have 4 components: Spark SQL, Spark Streaming, Spark GraphX, Spark MLlib. And the data are reading from different types of sources, such as distributed storage system, HDFS, S3, or even from RDBMS, and also from the other non-SQL systems, such as Hive, HBase, Cassandra. And so that's a brief view of the Spark. So idea of Spark is that, well, we can we need to design a system for expressive design an expressive computing system, not limited to MapReduce model. Instead, just MapReduce, we have more functions need to be supported, and we will facilitate the system memory, and we avoid saving the intermediate result to disks. So that's what happened in MapReduce. The map will write intermediate result to disk, and then reduce task will read the data from disk. But in Spark, the intermediate results will be stored in memory, and it will cache data for repetitive queries. So you can, if you believe that this piece of data is very important, you can decide to cache data in memory, but you cannot cache too much data, because if your memory is limited, right? You cannot cache too much data in memory, otherwise your computing resources will not be enough. And Spark will also layer an in-memory system on top of Hadoop. So this just means that utilize the Hadoop HDFS for data storage and achieve the fault tolerance by re-execution instead of replication. So I will try to explain this later. So in MapReduce, the major mechanism for achieving fault tolerance is by replication. And in HDFS, so the data will be split into different chunks, and each data chunk will be replicated for 3 times. So 3 is by default. You can also configure this number, but normally we will not change this configuration. So which means that each data chunk will be replicated by 3 times. So when there is something wrong with our data, so this piece of data is lost, but you have another 2 replications, right? You have another 2 copies. So you can go to another 2 copies location to fetch data, and then you recover data. So that's for the disk failures. And if your map task fails, so the master will know that on some nodes the map task is not finished successfully. So it will also try to invoke to do the map task again, and this kind of the MapReduce will use this kind of mechanism to guarantee the fault tolerance to deal with the failures. But in Spark, it's quite different. In Spark, data is not replicated. So if it uses HDFS, well, okay, so in the lowest level, the data is still replicated. But upon HDFS, in Spark, within Spark, there's no data replication, which means that the data in memory has only 1 copy. There's no more than 1 copy. So it's different in MapReduce. And If there is something wrong with the data in the memory, for example, in this node, some data is lost because of the computer failure, and instead of by fetching the data from the other copies, because there's no replication, you are not able to do that, but you will re-execute all the operations to generate this piece of data, and which means that so in Spark, it will keep track of all the executions. So instead of, so this is used to recover the lost data. So for at some point, if this piece of data is lost, and then according to the execution record, so Spark will re-execute all the operations to recover the lost data. So that's the basic idea of the Spark in Spark to achieve fault tolerance. We will see an example in the later slides. The Spark workflow is simply, you can simply think like this according to this figure. And you will have a driver program. So this is like the main function in MapReduce. And in this driver program, you will create a Spark context object. So this is the entrance for your applications to communicate with Spark. So each Spark program always need to first create a Spark context object. And this will tell Spark how and where to access a cluster. And also, it will connect to several types of cluster managers. So in Spark, it can use Yawn as a cluster management. And Methods is another cluster manager. And Spark also has its own manager for cluster and resources management. And you can configure this, so which one to use. And for cluster manager, it's mainly used for allocated resources across applications, the memories and CPUs, and for your Spark subtasks. And for the Spark executor, they will run communications and also access the data storage. So the cluster manager, if you go through this branch, it means that your Spark program is employed in a cluster. And based on this cluster manager, so your task is divided to subtasks, and each subtask will be sent to one worker. And within the worker, Spark executor will do some computations and access the data storage, and also the results will be generated and stored in memory. And there's also a local thread, so which means that you do not use a cluster. You can just use your own machine to do some kind of computations. But it's mainly used for testing, not for a real computing environment. A more detailed data flow is like this. We have the worker nodes and executors. The worker nodes are the machines that run executors, and each worker node will host one or more workers. Normally, there's one JVM for each worker, and each worker can spawn one or more executors. It's like this. So in the worker node, you can have more than one executors. So we have so each worker can have more than many executors, and the executors will run the tasks. So you can see here, and the tasks are run in child JVM for in each process, and execute one or more tasks using the threads in a thread tool. So that's basic, the detailed data flow in Spark. And if you are interested, you can read more details about this part in the Spark homepage. But I have to say, I'm also not quite familiar of this part because it's too low level, it's too system level. That's what Spark and MapReduce try to hide from us, right? So as programmers, we only need to focus APIs instead of going into the details. And there's also a master node to control the communications between the different worker nodes, and also to control your job running status. Okay, so that's a basic introduction of Spark. But before moving to the next topic, and I need to give a brief introduction of Scala, of this programming language, because next part, what we are learning is called RDD. The RDD is the foundation of Spark programming. So all the data is stored in RDD. But the RDD operations, if we need to know some kind of Scala knowledge first. Otherwise, it's not very easy to explain the RDD operations. Okay. I think most of you have no experience or knowledge about Scala. So, which means that you need to spend some effort on learning Scala on your own by yourself, okay? Because the 3 labs and 2 projects are based on the Spark, which means you need to use Scala for the programming. And also in the final exam, there's 1 question on Spark programming. And in that part, you also need to use Scala to answer the questions. So I hope that you can get some time to learn Scala programming. But anyway, if you are already familiar with Java programming or Python programming, I think it's not very difficult task to learn Scala. Although it's still very different because Scala is a general purpose programming language to support both objective-oriented programming and also functional programming. So if you have learned C++, or Java, or C#, these are object-oriented programming, sorry. And for OOP, it's very different from functional programming. In OOP, the idea is that you can view each thing as an object, right? You write a class, and this class is used to represent some concepts or represent some entities, if we say that from the database perspective. And in functional programming, the basic unit is functions. It's not objects. So that's very different ideas of writing programs to solve the tasks. And in Scala, it supports both OOP and functional programming. And it can be used as drop-in replacement for Java. Actually, you can mix the Java and Scala programming in one project. You can have both Scala program and Java program in the same projects. And you can also use existing Java libraries, use the jar files to write Scala programs. And also you can use existing Java tools for compiling your Scala projects, such as Ant, Maven, JUnit, etc. You can also use the IDE support, such as NetBeans, IntelliJ, or Eclipse for the Scala programming. So actually Scala and Java, they have many things in common. So that's why I said if you are familiar with Java, it should not be a difficult task to learn Scala. And why Spark choose Scala? Well, it's I think the major reason is that because Scala supports both object-oriented programming and functional programming. And for OOP, so every value is an object in Scala, and every operation is a method call. So this is just the same in Java, right? And the language supports advanced component architectures through classes and trees. So trees are just like interfaces in Java, but it's called trees in Scala. Scala is also functional programming, also supports functional programming. So it supports functions and immutable data structures and preference for immutability over mutation. Well, we will see some more features about functional programming part in Scala in later slides. And it is seamlessly integrated with Java and being used heavily for big data analytic problems. So Spark is just one of its applications. It also has some other applications for big data problems. In Scala, the basic syntax is, okay, we have object, it's the same as in Java, and we have class, also the same as in Java, and methods, also the same as in Java. So you can define own class, and in the class, you can define some methods. And fields, each object has its unique set of instance variables, which is called fields. And an object state is created by the values assigned to these fields. And trees are just like Java interface, and a tree will encapsulate some methods and a few definitions, and which can then be reused by mixing them into classes. So according to the definition, you can see it's very similar to the Java interface. And I think these concepts are very easy to understand, and the most difficult part is the last one, which is called a closure. And a closure, this concept is in functional programming. The idea is that a closure is still a function, but its return value depends on the value of one or more variables declared outside this function. So think about what you have learned in OOP about the function about OOP. A function will receive some parameters, right? And it will return some values, and that's what the function does. And now for closure, the major difference is that the return value does not just depend on the parameters received by this function, but also depends on some values, some variables declared outside of this function. So which means that actually closure is a function plus environment. And environment is used to represent these variables declared outside this function. We will see some examples later, and I hope that could help you to understand what is closure, because in Spark programming, actually, most of the Spark tasks are a kind of a closure. So first, let's start from some simple concepts of scalar. It's statically typed, so you don't have to specify type in most cases. Scalar has a type inference. So for example, you define VL, which means value, sum equals to 1 plus 2 plus 3, which means that the type of sum is actually integer. It's based on the type inference according to our expression. And if define VL names is equal to list, so by default, it's explicit type actually according to type inference. Names is of a type list containing a list of integers. So this is just according to the value assignment for this names variables. And map. So according to this definition, and based on the type inference in Scala, it will give a type for map as this. So you don't need to give explicit data types when you define a variable. So that's difference between Java and Scala. Because in Java, you always need to give a data type for variable, right? Int, double, or some according to your own your self-defined class. So you always need to do that. But in Scala, there's a type inference. Okay, and Scala is high level. So in Java, if you want to check if the string has an uppercase character, you need to do this, right? You need to have a for loop. You need to enumerate the characters in the string. So for each character, you need to check if it is uppercase. And if so, you set it to true and break, and otherwise, you will need to check the next character. So this Java code. But in Scala, you can just write one line to do this task. So name is a string, and you check name.exists underscore dot is upper. So underscore is featured in Scala. It has very flexible usage in Scala. And it's mainly used to represent the parameters of a function. So exist is a function. It's used to do a check. And so underscore is used to represent each character in the name string. So this actually means that to check if in name there exists one character which is uppercase. So if so, it will return a true, otherwise it will return false. So you can see for Scala programming, the codes you need to write is much, much shorter than Java because of the functions supported in Scala. And Scala is very concise. So it's about class definition. So if you define a person class, so in Java, you need to give the member variables, name, age. You need to get the getter and setter for them. And you also need to give the construct function. And in Scala, well, it's just like you can save a lot of space, actually. You also have the same class and the same member variables, name and age. But you don't need to define so many functions to do the same jobs. And you just need to do like this, so that's all. Define age, which is equal to underscore age. It means that it will receive the value from the parameters of this person class. And so more detailed grammars of Scala, you can check the website I provided in the reference slide at the end of this lecture slide. So there is a brief introduction to Scala grammar, and you can see a lot of examples there. Another important concept in Scala is the difference between variables and values, which is represented by var and val respectively. So variables are values stored that can be changed. For example, you define var full as to this string, and later you can assign a new string to this full object. It's okay because it's a variables which can be changed. But for values, which means they are immutable. So variables are mutable, but values are immutable, and that represented by val. So if you define val full to this string, then you cannot assign a new string to this full object. That's not acceptable by Scala. So it's kind of like a final object in Java, right? So that's variables and values. Scala is pure object-oriented, which means that it supports object-oriented programming. So every value is an object, so called pure object-oriented. Even integer is an object. So 1.toString, and you will convert this integer to string. So you can see that 1 actually is already an object. But in Java, you need to first use integer class. You need to use integer class to do this. You cannot just use 1.toString in Java. Every operation is a method call, actually. So 1 plus 2 plus 3 is the method call for this brackets, and then plus, that's a chain function. And because you can omit dot and brackets, so finally the expression can be like this. And similarly, for this, abc dot character at 1, which means you need to get the first character in this string, and you can omit dot and brackets, so it will be like this. And classes are just like Java, and you define a class language, and in this class you have some members. So you have a value name, and this name is of type string, and then you can have some functions in this class. So that's similar to Java. And also you can extend. You can get some class by by the existing classes. So Scala extends from this language class, and you can also have anonymous class. So like this, Scala is equal to new language Scala. So this is just an anonymous class. There's no name for this class, but it is a class actually. Okay, so we have a short break, then we move to some more advanced topics about Scala.
是上面的，就是把那个 y 这个不是预期的，就是真实的，对，代进去乘以这个 w 这个 x， 对，对。社会，对对对，政府主义，这个就是那个，这个东西就是，但是也可以一样，也可以，就是看你怎么定义，就是说，看你怎么定义，可以是有些是定义是负，有些定义就是看你怎么定义了。但是你如果说定义成零的话，你什么东西只当你100%都是零。对对对对对对对对对。它这个的话，就不是通过这两个110是负1，就是看这个，你这两个如果是0的话，对对对，就是这个。对对对。其实它就是你这得出来了，就是经过这个active function，然后它 active function 不是有一个设定大于0的话，就是一个1小于等于0的话，可以为0或者负1，那就是看你怎么设定的。那它这个就是不严谨。对。对啊。end。对啊，你这可以理解为0吧？就是你它像真值表。对。你怎么纠结这个问题？它这个00真值表不就是00得0，and 的话00得0，01就1得1，然后这个是表示是 or， 这个是 or。没有必要纠结这个，因为的话，它有些它是看设定的，有些的话它就是用0表示 not， 或者有些是用负1表示 not， 用1表示，反正1是表示 yes， 就是0或负1表示 not。 3个题里面有那个解释，第4题有解释，没有解释。我昨天有同学跟我讲，他说有解释的，我说怎么没有解释？对，这个我也看，这是第5题。
Okay, so let's continue. So this is an example for the scalar trace. So as introduced, trace is like interfaces in Java. So for example, we can define a trait, JVM. And the difference is that in scalar traits, they allow the implementation. So we define a trait, JVM, and then we have function toString. So first we will invoke the super toString and plus runs on JVM. And we have another trait called static, and also has a function toString. And the toString function is defined as the superclass toString plus is static. And now we have a class scalar and extends language. And so remember that, where is language? Here. We have class language here. The language has a member name of type string and also has a function toString. So class scalar extends from language, and which means it has a name variable. And in this scalar class, name is assigned by a scalar value. And with 2 traits, with JVM and static. So traits are stackable. So first in, first in, last out. Now if we use print line, new scalar, new scalar object, it will print the following things. So first is scalar, because it is it extends from language. And when you use print line, it first invoke language toString function. And toString function will print name. So the scalar is first printed out. And with JVM and with static. And so with JVM, then according to this order, so first we will go to this function. We'll go into this function toString. So scalar runs on JVM, then static is static. So finally, the result is like this. You can extend from existing class and with some traits defined in scalar. So it's just like implement some interfaces in Java. And so that's about the OOP part. So it should be easy to understand because you already have learned Python or Java. So that's not a problem. And I think the major difficult part comes from this functional programming perspective in Scala. So Scala is a functional. In functional programming, there are some basic concepts as well. So first is called first-class functions, which means that the functions are treated like objects. So this is supported in Scala. Which means the functions are treated like objects means that you can do the following things. So first, you can pass in the functions as arguments to other functions. So these functions can receive parameters which are functions actually. So this is in functional programming. And also you can return functions as values from other functions, which means that the returning value of a function is also a function. Okay, it's not a data type, not a data, it's a function. And you can also assign functions to variables or storing them in data structures. So these 3 things cannot be supported in Java, right? in OOP, in object-oriented programming, because nowadays more languages try to support both functional programming and OOP. I'm not sure if Java 8 has some features for functional programming. This is an example for the lightweight anonymous functions. And we have a function to increase the value of a parameter by 1. And a lightweight anonymous function can be defined like this. X, which is a parameter of this anonymous function. And the parameter data type is integer. And the function body is this part, x plus 1. And the return value is x plus 1. So now you can assign this anonymous function to a value. So this value is equal to this function. So now actually plus 1 is a function now. So you can use plus 1 and give a parameter to this function, 5. So the result will be 6, because according to the definition of this function, and the value will be obtained by 1 plus the parameter received by this function, and the return value is 6. So you can see that one value can be a function as well, instead of just objects. So the functions can be treated like objects. And the parameter here, this x, actually can also be a function, but not in this example, because in this, it can also be a function, it's okay. So both the parameters and the return values of function can be functions as well. And you can also assign this function to a variable to store this function. Okay. And now we see the examples for the closure, which is the most important concept in Spark. So the closures, a closure is a function whose return value depends on the value of one or more variables declared outside this function, and also the parameters of this function. So we can first have a variable full, and this variable is value 1. So this is variables declared outside function, this function, plus full. So plus full is defined as an anonymous function. In this anonymous function, it takes x as the input, which is integer. And the function body is x plus full. And full here, this full object is declared outside of this function, right? So we can call this plus full as a closure. If it's x plus 1, then this is just a function, because the function, the return value of this function only depends on the parameter it receives. But now it's x plus full. So full is declared outside this function. So now it is called a closure, because it's a function plus environment. A function x plus variable declared outside this function plus full. And as a result, you can change the variable declared outside the function to get different return values. So plus 4, 5. Now because 4 is equal to 1, so you can get value 6. But if after you change the value of 4 to 5, you still invoke plus 4, 5, but now the value is 10, right? So you can change the variables outside this function, and then to obtain different return values for the same function call. So that's about the idea of closure. Functions plus the environment, so definition of a closure. In functional programming, another concept is called higher order functions. The first one we have learned is called first order functions, first class functions. These can do these operations. And the higher order functions is that a function that does at least one of the following. First, it takes one or more functions as arguments, and it returns a function as its result. If one function does at least one of the two things, then it is called a higher order functions. It's very obvious. According to the name, you know the order is higher. It's not a normal function, because the parameters of this function are functions as well, or the return value of this function is also a function. So that's why it's called higher order functions. And this is one example. So we define an anonymous function and assign this anonymous function to +1. So now +1, this value is a function. And we define a list names has 3 integers, 1, 2, 3. And now map takes a function as the input, names map +1. And so this will map from integers to so now +1 will take each integer in this list as a parameter and then generate a new list. So names map +1 is a function, and this function is a parameter for this map function. So you see, so map is a higher order function, okay, and this +1 tells map how to convert the data. So +1 will take each integers in the names this data structure, and then +1 for each of the members in the list, and obtain list 2, 3, and 4. So map is called a higher order function because it receives a function as a parameter. And you can also have inline anonymous, which means you don't need to define a function like this. You just use an anonymous function inside the bear case for map. So x to x +1. This is an anonymous function. And this anonymous function will be applied to each member of the list by this map function. Then you also receive this result. And for short, you can also use underscore. So underscore is, as I said, it has a very flexible usage in Scala. So underscore is used to represent the parameter of a function. So underscore, actually, it will represent each member in this list. And +1 will be applied to each member. So you also get this result. So in Scala, you have very flexible expressions to do the same thing. So in this example, you try to increase the value of the members in the list by 1. So you can either first assign this function to a value. So now this value is used to represent this function. And then you pass this +1 value to this map function. Or you can also have a inline anonymous function, which is a parameter of this map function. And you can also use underscore to represent this anonymous function. So I'm not sure if this is clear to you, or if you have any questions about this part, about the closure, about the higher order functions. Okay. We have some more examples on the higher order functions. So we also have a list with 4 integers. And now this is used to check if there exists some members in this list is equal to 2. Because we have an integer 2, right? So this result is true because in this list there's 1 member which is equal to 2. And names find underscore equals to 2 is used to find the position of the value 2 in the list. And this is index pair to find the position because 2 is 0, 1, 2, 3. Right? 2, this value is at the first the position 1, so it will return 1. And find is used to get if there's similar to this exists. The result is sum 2 to tell that you have a 2 value in this list. Functions can also be used as parameters. So we can define a function called call. In this function, it takes a function f as a parameter. And the function body is just f1. So 1 is a parameter for the function f. So assume that we already have a +1, which is defined here, +1, which increases the parameter received by value 1. So if we use call +1, so now we check what we can get is we have f is equal to +1, right? And then plus 1 get parameter 1. So 1 plus 1 is value 2. So that's it. And the other two calls of the function call is actually they also do the same thing because they are all about the same function. This is about inline anonymous function definition, and this is used you use underscore to define an anonymous function. Call is also called a higher order function because first it receives a function as a parameter. So this is a function, and the data type of this function is it takes an integer as a parameter, and the return value of this function is also integer. So that's about parameter. And the return value now it depends on your function received. Okay, it will the return value is also it's an integer because it's received f as a parameter. But what f will do is not known in this call function. You can receive different types of f in this call function, and the return value will also be different. So for example, here plus 1, you can also have a plus 2 function. And if you call plus 2, then the result will be 3. Now you can try to remember MapReduce. Actually, map and reduce, they are also kind of a functional programming. So I didn't mention that MapReduce, the idea actually comes from functional programming as well. So map and reduce are two basic functions in the functional programming. So map is used to convert the data from one type to another, from one format to another format. And reduce is used to do kind of aggregation in functional programming. So the Hadoop MapReduce adopt these ideas of functional programming and have this kind of computation model. In MapReduce, so map, what will map do? You define something in the map function, right? And you define something in the reduce function. You can assume that actually the map function receives a function. The reduce function also receives a function, actually. And what you can do within map and reduce depends on what you send to the map function and to the reduce function. And the whole structure of MapReduce is just a framework. And what it can do, it depends on the functions you send to the map, you send to the reduce. So that's also about the MapReduce design actually also adopts some ideas from functional programming. And in Spark, it's more obvious because not just of map and reduce, more functions are supported in Spark, as we can see later when we learn RDD. Now, let's look at this example to see if we can understand higher order functions and also the closures. We have a function called base function. And we have anonymous function, which is very complicated, right? So this is a whole function body. This function takes x as an input, and x is an integer. And what does the function do? This is the function body. And within the function, it is also a function. It is another function, y. Takes a parameter y, which is also an integer. And it will plus x and y. You can interpret this line as, this is more clear to you. It's more easy to understand. So we have a function, base function, take a parameter x as the parameter. And within the function body is like this. We have another function called sum function, and takes y as a parameter. And it returns x plus y as a result. And then we return this function as a result for base function. Okay. Now we can see that actually sum function, this function, can be called a closer, right? Because it has the return value of this function depends on a variable declared outside this function. It depends on x, but x is declared outside some function, right? So this is called the closer. And that's why we can define closer 1, closer 2 by calling base function 1, base function 4. So base function 1 is actually some function y, but with value x to 1, right? And for closer 2, which is base function 4 with parameter 4, and this is actually also some function y with parameter y, but the x value is 4, right? So we have two closures. And so for the results, closure 1, 5, and closure 2, 5, they both take the same parameter 5, but the results will be different, right? So what will be the result? Actually, it's very obvious. It's 6, right? And for this closure, the result will be 9. It's 5 plus 4. And if I hide this part, I believe that it's very difficult to understand this line, right? It's very complicated. So in Scala and also in functional programming, when there's closures involved, sometimes it's not very easy to understand because of these higher order functions. And one value, it may be an object, but it may also be a function or a closure. So in this example, it is a closure because this closure, the result of this closure depends on the parameter you give to it. And it is a function plus a variable declared outside this function. So that's the definition of this closure. Okay. Oh, there's some explanations. So because base function returns a function, so this base function is a higher order function, and according to the different parameters it takes, so closure 1 and closure 2 are two functions, but there are also two closures because they have their return value is depend on one variable declared outside of them. And although they refer to the same function, base function, both two closures refer to the same function, but associated environments are different, right? Which one is 1, another one is 4, so the results are also different. So the higher order functions are one of the most important features in functional programming. And last one is about the usage of underscore. This is a very, so at the beginning it's not very easy to understand what does underscore represent. So according to these examples, then you can have a rough idea about the underscore. So for example, names, remember that this is a list. Map, so map is applied to each member in the list. And according to this function will increase the value by 1. And this is an anonymous function. And underscore is used as a placeholder for the parameters. So remember that x actually is a parameter. So underscore is used to replace this parameter x. And x to x plus 1 is, for short, is represented by underscore plus 1. So underscore is just a parameter x. So that's one usage for the underscore in anonymous functions. And this is another example, list for each print. So you can see that for each is also a higher order function, right? Because it takes print, this function, as a parameter. And print underscore. So underscore is used to represent a parameter, a, okay? So actually it represents a to print a. So you can see how underscore is used as a placeholder for the parameters. You can use 2 or more underscores to refer different parameters. So this is more complicated. So this is one example. Value sum is equal to list 1, 2, 3, 4, 5 dot reduce left underscore plus underscore. So these 2 underscores are used to represent 2 parameters. It means that it represents an anonymous function which takes 2 parameters, okay? And as shown here, this anonymous function is like this, takes 2 parameters, a and b, and it will do a sum. And the function body is a plus b, return a plus b. It takes 2 parameters. So reduce left will just do the sum, 1 plus 2, and then the result 3 plus 3, the result is 6, plus 4, get 10, and plus 5, get 15. So that's the final result. So the reduce left method works by applying the function operation you gave to it. So this is a sum function, and applied to the successive elements in the collection. And so you can see reduce left is also a higher order function. It takes a function as a parameter. You can see more examples about underscore in the other slides when we learn Spark programming. So most of the times that used to represent the parameters, either represent 1 parameter or represent 2 parameters. So in the labs, you can also see some examples. You are going to use Spark Scala to solve some problems, and you can use the underscore to write the program to solve the problem. Okay, now we are ready to move to the next topic. For the Scala part, I have to say this is a very, very brief introduction. And just mentioned about the OOP part, the object-oriented programming part, and the functional programming part of Scala. But as a programming language, Scala is more complicated and complex. So if you are interested in Scala, you need to at least you need to read the reference I gave to you, which is at the end of this lecture slide. You will learn more grammars of Scala and see more examples and know more know more functions you can use in Scala. According to the previous year's experience, giving you a problem, and if I ask you to solve this problem by using Spark Scala, the problem is not about how to write algorithm. The algorithm actually is very easy. The major problem is that you are not familiar with the Scala functions, and you don't know which functions to use in Scala for this Spark programming problem. So that's a major problem. And what I can suggest is that just by practicing more and more, so you can be more familiar with this language, and also with Spark, more familiar with Spark. And then you can, given your problem, you will have an idea of which function you need to use to solve this problem. For example, for each and reduce left, these functions, if you have never used them, then you don't know if they can be used for a given problem, right? So you need to, at least you need to practice you need to practice these functions in many problems, and then you know for which kind of problems, what kind of functions in Spark, in Scala you can use. So that's it. That's about Scala introduction. So now we can move to the next part called RDD introduction. RDD is a foundation of Spark programming. So all the data operations are based on RDD. So in a Spark program, first time you need to read the data from disk to memory, right? Then the data actually is stored as an RDD in memory from disk into memory. Then next, all the operations are based on this RDD, this data structure. In Spark, the major challenge comparing to the existing systems, well, existing in-memory storage systems have interfaces based on the fine-grained updates. For example, it can read and write to cells in a table. So that's for existing in-memory database. And also key-value stores, or distributed memory, distributed processing system based on memory. They also have they all have the fine-grained updates. And also, it requires replicating the data or logs across nodes for fault tolerance. In memory, each data also needs to be replicated for 2 or 3 times to guarantee the fault tolerance. But this is expensive. Because your memory is limited, so most of the times these copies are not maintained in memory, they are stored in disks. And as a result, if some of the data is lost, then you need to go to disk to fetch data, to read the data back from disk to memory. But which means this is much slower than the memory write, right? So in MapReduce, it just uses HDFS and then read the data from HDFS to memory in the map function reduce function. And that's it. It does not utilize memory. But in Spark, the idea is to utilize the memory to achieve a powerful computation, to achieve efficient data sharing. So the challenge here is then how to design a distributed memory abstraction that is both fault-tolerant and also efficient. So that's a basic, the most important challenge in Spark. We need to use memory, and this is a cluster, right? So it's a distributed memory, not memory on a single machine. And you need to guarantee fault tolerance, and you also want to get efficiency. And for existing systems, they can get fault tolerance, but the problem is that they're not efficient because of this mechanism to guarantee the fault tolerance. So in Spark, they try to solve this problem in a different way, and they propose a RDD concept called resilient distributed dataset. And from the name, we can see the three words, right? Resilient, distributed, and datasets. So the three keywords already represent the features of the RDD data structure. So first, the distributed RDD is a distributed collection of objects that can be cached in memory across cluster. So the RDDs can be cached in memory, and this is a distributed memory, not memory in a single machine. So it's in memory across the whole cluster, and it can be manipulated through parallel operators. So that means that the data is already partitioned into different parts, right? And each part is held in the memory of one computer, and then the operations can be applied to these parts, different parts of data in parallel. And it can automatically be recomputed on failure based on a concept called lineage. So the data recovery is not based on replication, it's based on re-execution. And the re-execution operations are recorded in a concept called lineage, which is order list of operations in order to achieve this piece of data. So once some data failure happens, then so Spark will check the lineage for achieving this data, for obtaining this data, and then to re-execute all the operations recorded in the lineage to get the data. And RDDs can express many parallel algorithms and capture many current programming models, such as MapReduce. So both map and reduce functions are supported by RDD. So which means that if this problem can be solved by MapReduce, then okay, it can be easily solved in Spark as well, because both map and reduce functions are also supported in RDD. And SQL type of operations are also supported in RDD. And also specialized models for iterative applications such as Prego to support graph processing is also supported in RDD. So RDD can also do something similar to Prego. They have some interfaces similar to support the Prego operations. And what is an RDD? So this is published in a paper in one of the best conferences, in the system research area called NSDI. This is a distributed memory abstraction that lets programmers perform in-memory computations on large clusters in a fault-tolerant manner. So resilient is about fault-tolerant, and distributed just means that the data are stored in different computers, and dataset is used to represent that. RDD is used to store the data. So for resilient, it's mainly about fault tolerance. So, RDD is able to recompute missing or damaged partitions due to the node failures. So if on one node something wrong happens on that node, and as a result, the data assigned to that node will be lost, right? So how to get data in that node? And RDD will try to record all operations on that node. So if it detects some failures from that node, so it knows that, okay, I need to get the data from that node, but now the data is lost. But I know how those data are computed, how those data are obtained. So I check the operations, and then I execute all the operations. Then I recover lost data in Spark. And distributed, well, obviously, it's very obvious. According to the name, the data resides on multiple nodes in a cluster. So in each computer, it has some memory, and then this memory will be used to store some partitions of the data. And data set just represent that a collection of partition elements will be stored in RDD. So RDD is a primary data abstraction in Spark and the core of Spark. So it enables all the operations on collection of elements in parallel. First, the data in RDD are partitioned into different, split into different partitions. And then the operations can be applied to the different partitions in parallel. Okay. The RDD has a following trees in memory. So you know that RDD is stored in memory. Because as a result, then we can utilize memory to do the data processing, which is more efficient than reading data from disk to memory. And it is immutable or read-only. So the RDD cannot be changed. You can only get the value once. After it's created, you cannot change the data. You can only transform the current RDD to a new RDD. Okay. And it is lazy evaluated. So the data inside RDD is not available or transformed until an action is executed that triggers execution. I will explain this later when we learn the RDD operations. And cacheable means that you can hold all data in a persistent storage, such as in memory or disk. Normally it's in memory because it's not useful to persist the data in disk. Normally we will persist data in memory, and as a result, next time when some other programs also need this data, so it can get data directly from memory instead of from reading the data from disk or do some replicate computations. And parallel is very important because both MapReduce and Spark try to utilize multiple computers in a cluster to improve the efficiency. So the parallelism is very important. Try to process data in parallel and process the different partitions simultaneously. And typed, so the values in RDD must have a type, such as integer, or long, or double, or string. All the data in the RDD must have a type. And partitioned, well, it's similar to parallel. So the data inside RDD is split into different partitions and then distributed across different nodes in a cluster. So that's why the data can be processed in parallel. This is just because data are partitioned first, and then they can be processed in parallel on different computers. The most important concept for RDD is about operations, because what we will do next is based on these RDD operations. So first, we will create RDDs, and then based on created RDDs, we have these operations to do the data processing. And there are two types of RDD operations. One is called transformation operation, and next is called action operation.
Because you mentioned that we just only need to read once from disk into memory and process that. So what if we know that the disk space is much bigger than the memory? What if the memory is not big enough?
In that case, you can only read part of the data into memory.
And then write back to the
Yeah. So in that case, Spark will not be very efficient because you are not able to read all data into disk.
So the difference between MapReduce and Spark is Spark that fully utilizes the memory, while MapReduce only utilize part of the memory.
So Spark try to utilize memory as much as possible. You can see that. You can see that.
Here's like a stripe, we said in that reviews. Actually, it behaves similar like Spark. Like we try to memory processing all the computations, right?
Sorry, what?
Because previously we mentioned the stripe method we use in that reviews. That one is in-memory processing. In that way, it's like similar like Spark. We do as much in-memory processing, right? Like Spark. The stripe method.
Which method? Sorry.
Stripe versus the pair.
Oh, Stripe. Okay.
Yeah, in that sense, is that similar to Spark? Doing much in-memory processing.
It's not similar to Spark, but the idea is that you use some memory to cache data. So from this perspective, it's similar because it both try to cache some data in memory. But caching data in memory is just one feature of RDD in Spark. So you can see the RDD tree. So cacheable is just one feature. The other features are also very important. Yeah, but you are right. So for the Stripe method, I try to utilize memory to hold some data and then to improve the efficiency, right? But that's not for data sharing. That's only for one computer. So in Spark, the most important problem is that all the data are stored in memory, and the data sharing is based on memory, not based on disk.
So the data will go directly through memory.
Yeah, to memory instead of to disk. Yeah. And about operations, two types of operations, transformation and action. So transformation will transform one RDD to a new RDD. So because RDD is immutable here, it's read-only. So after you give some value to this RDD, and then it cannot be changed. You can only transform this RDD to a new RDD. And at this stage, actually nothing gets evaluated when you call transformation function. It only takes an RDD and returns a new RDD. Okay, that's called lazy evaluation. This is one feature of RDD. And transformation functions include map. So just similar to the map function in MapReduce, it will, according to the function you gave to the map, and it will transform your data to another type of data. Also remember the examples in the previous slides, given a list, and then you can invoke list.map. According to the function you gave to this map function, you get a new list. And filter is used to filter out some results according to some predicates, to some conditions. Flat map, similar to map, but it's different. So we will see the difference later. Group by key, it will group the key value pairs according to the keys, and then values will be grouped together as a list. And reduce by key, so we'll do some kind of reduce jobs according to the keys. So reduce by key is similar to the reduce function in MapReduce. And aggregate by key, do some kind of aggregation, also according to the function you gave to this function. And join, similar to join function in the database. And this is for transformation. So you just need to remember that transformation will convert transform one RDD to a new RDD according to some function. So that's transformation. This is RDD. According to your transformation function, then you get a new type of RDD. And for action, action is different from the transformation operations. It will evaluate and return a new value. Remember that now it returns a new value, not an RDD. So that's a difference between the actions and transformations. Transformation, the return result is still an RDD, but for actions, the return result is a value instead of an RDD. Okay, and when action function is called on RDD object, so all the data processing queries are computed at the time, and the result value is returned. So remember that when you invoke the transformation operations, so nothing will be evaluated. Only when you give an action operation, then all the transformation operations will be evaluated, will be executed in order to get the result for this action operation. And the action operations include reduce, collect, count, first, take, we will see what does each of them mean. So the reduce, also similar to the reduce function in, I made a mistake. So reduce by key is not similar to the reduce in MapReduce. So this reduce function is similar to the reduce function in MapReduce. And collect, count, first, take, count by key for each is used to iterate over each data in the RDD. So the difference between reduce by key and reduce is that, so reduce by key will do some kind of aggregation based on the keys, but the result is still the RDD, okay? The result is still RDD and of type of key value pairs, so that's a reduce by key. But for reduce, it will do some operations on RDD and compute the value. As the result is not an RDD, it's a value. So we will see the differences between them in some examples in the later slides. So what you need to remember now is that for a Spark program, okay, you first need to use RDD to store the data you read from disk in memory. And then based on the RDDs, to do the data analytics, to do different jobs, you have transformation operations and action operations. So transformation operations will just transform the RDD to a new type of RDD. And action operations will do the real evaluation on the RDDs and also will cause all the previous transformation operations be executed and to get the final result. So this is an example. So first we create an RDD from data source, such as from HDFS or from local file systems. We can do this by parallelizing existing collections, such as lists or arrays, or by transforming existing RDDs or from files in HDFS or local file systems. Then we apply transformations to this RDD, such as map or filter. Assume that we can have a list, and we parallelize this list to RDD. Now this list is stored in the RDD data structure. And by applying filter function, so we will filter out some some data that do not satisfy the filter conditions. So only filtered RDD will be kept. But remember that this is not evaluated at this stage because the filter is a transformation operation. It's not action operation. And map will map the filter RDD according to the function to a new mapped RDD. So finally, when we reach collect, now collect is an action operation. So all the operations, filter, map, and collect will be executed at this stage. So this is called lazy evaluation. And then the RDD is filtered and mapped and then collected to get the final result. So in your Spark programming, if you do the Spark programming in the Spark shell, you can see that if you do some transformation operations, the feedback is it's almost instant. It just shows you that, oh, okay, it is successful. Because actually at this stage, nothing happened. It only recalled what operations needs to be done at this stage and what kind of data types are changed across different RDDs. And when you do some action operations, then you see that you need to wait for some time because the data processing actually happens at this stage. And after maybe several seconds, then you can see the results. You can see the value instead of the RDDs. And the users, we can control the other aspects. First is about the persistence. We can decide which data can be persisted in memory, can be cached in memory. If we do not cache the data in memory, then after it is computed, it will be discarded in memory. It will not be stored in memory. Which means that next time, if we want to use the same data, we need to do the computation again. But if you persist the data in memory, then okay, it will be stored there. And next time, just need to read from memory. That's it. And next is partitioning. We can decide how many partitions we want RDD to use. So for example, we can give 4 partitions. So this list will be divided into 4 partitions. And these 4 partitions will be processed in parallel. That's what we can control but other parts are controlled by Spark. And this is an example about how you can create the RDD in a Spark shell. For example, we can create RDD from a file in HDFS. So we use text file. So Spark context, this is object. If you use a Spark shell, the Spark context object is already created for you, so you can just use it directly. But if you write Spark program not in a Spark shell, you also need to initialize this Spark context object. And using this Spark context object, and we use text file, this function, to read a file into from disk to memory. And we give number 4, which means the number of partitions. We will split the data to 4 partitions. Then this is a text file. So this is lines of strings. For example, if you use PG100 TXT, you know what it's like, right? It's a line of strings. So if we do this, Spark shell will show us, okay, and we create an RDD, Spark RDD of type string. Okay, have partitions, have 4 partitions. Oh, sorry, I didn't use partition here in this example. But if you have 4 partitions, 4 here, then you also see the number of partitions. And this RDD is used to store this PG100 TXT file. Okay, but remember that at this stage, actually the file is not read from disk to memory now because of the lazy evaluation. It just record operation here. And we can also use other ways to create RDD, such as turn collection into RDD. We can parallelize a list or array into RDDs, and or from existing some Hadoop input format. If you remember what is input format, this can be obtained from Hadoop, using the Hadoop file to get key value pairs and stored in the RDD data structure. Okay. See some examples of the Spark transformations. And these functions can be used to transform the RDD to a new type of RDDs. Okay. Remember that for transformation operations, they use lazy evaluation. So the results are not computed right away. So instead, in Spark, it remembers the set of transformations applied to the base data set. And then the Spark will optimize the required calculations. Okay, there are some optimizations in Spark. And based on the record of these transformation operations, then Spark will also recover from the failures. So the fault tolerance is achieved by this re-execution instead of by replication. So the most widely used functions are listed here. So map function, filter, distinct, fact map. And well, without examples, it's hard to explain what does the mean, what does each of them mean. So filter is easy to understand. The filter is used to filter out some results according to the function you gave to this filter function. So this is a condition you specified. So only the data satisfy this condition then can be reserved. Otherwise, it will be thrown away. A map is to, according to the function you gave to this map function, and then it will transform your data to a new type. And distinct is used to count the distinct data elements in the given RDD data set. And flat map is similar to map, but it will be used in the word count example. So we can see the difference in map and flat map in the word count example. So actions, there are some examples of actions operation, reduce, similar to the MapReduce function. And take is to take the first n elements, and collect will just return the data in the RDD as an array. And take ordered is used to, first it will sort the data in RDD according to some order, and then takes the first n elements. Okay. And remember that the action operations will cause Spark to execute all the operations. Okay. And it is a mechanism to get the results out of Spark. So in Spark, all data are in format of RDD. But if you want to see the results out of Spark, you need to use action operations to do some operations based on the RDDs and then get the values, such as the result will be just one value, a single value, or a list of values, or an array of values, or some other type of values. But anyway, they will be values instead of RDDs. So that's a difference. Okay, so now later we will see one example about how to use these operations to do some tasks. So we first have a short break, and then we will come back to continue.
low balance，但如果你低于它的话，你说实在电脑里它那我不知道它 Spark 会怎么样处理这种情况。这个应该在 Spark 那个如何配置 partition 的地方是有解说的，但是我现在不是决定，我要去查一下，我去查一下，一般我们这个还是应该是怎么定义？如果我知道它，知道它的那个是多少个小子在那边，还是要确实还是要结合或者 class 里面多少 node 去定义，一般是这样子。但是就是说你需要定义成多少去有一个比较好的结果，大家也都是通过实验去，也没有说其实就像MapReduce那边一样，MapReduce的时候就 Map 跟或者 MapReduce 可以是多少，你是实验测出来的，就也不太好讲。它很简单，这个词可以让你 customize，就是因为有些有些地方它也for this cause，因为这个原因才让你 customize。应该也不是因为 Webpack 的问题，应该是 Webpack 的。那就很奇怪，我觉得这一点，因为它这个 master 的肯定是知道多少，它肯定是知道自己的 offset 最好，这个让那个 user 去 customize 这个跟那个 MapReduce 确实不太一样。MapReduce 的话就是说是找，对，它去找这个就是很好的，对，但 Spark 的话是你自己可以控制它的难度，对，这个完全是确实是一个比较实际的一个应用。我也去看一下，就是说怎样是一个比较优的设置，因为这个确实没办法给出一个理论上的，就只能也是说根据你的 cluster，然后根据一些就是heuristic 的一些实验的经验，然后去看说像去考虑的。谢谢。
Okay, so now we have learned RDD and RDD operations. So now let's use some examples to try to see how we can use these use RDD and RDD operations to do some big data analytics problems. And this is one example. So assume that we have a huge number of logs, and that log will represent all the messages generated from the computers. And now if a web service is experiencing some errors, and now assume you are an operator, and we want to search the terabytes of logs in the Hadoop file systems to find the cause. And what we can do, we can use the Spark to transform the data to RDDs, and then use RD operations to find the errors. So assume that the error will be logged as starting by a line with error, and we want to check if this is caused by HDFS. Now we can see first we get lines RDD. So this lines RDD is created by using this text file operation to read the file, the text log file from HDFS. So we gave the position, the location for this HDFS file, and then the file will be transformed to the lines RDD. So all the text are stored in as string lines of strings in this lines RDD. So that's for the base RDD. And next, we want to find the lines starting with errors, because only these lines give some information about the errors, right? So we define another RDD by transforming the lines using the filter function. So filter underscore start with error. So underscore, remember, it represents a parameter of this function. So which means actually this is x to x dot start with error. And only a line can starts with this error, with this word. It will be kept in this RDD. Then other lines will be discarded. So now this is the errors RDD. Remember that by this stage, nothing happens. This transformation operations, and because of lazy evaluation, and we are not reading the data from disk. and we are not transforming the data from lines to errors. Spark just record these operations, okay? And errors persist. Persist will cause that these errors already be persisted, be cached in memory. This is because we need to do different operations using the errors RDD. And if you do not persist errors in memory, then for the next time when some other operations also needs the errors RDD, you need to get the errors from the base RDD again and to read from disk again, so which is not efficient. So that's why we want to persist errors in memory. So we have persist. Then errors count will count the number of lines in the errors RDD. Count is an action operation, okay? So at this stage, now all the operations will be executed. So first, it will be read from HDFS, and then we do the count operation. So this line is just transformation operation. And this line is used to persist errors RDD, and nothing will happen. And this line counts, then the action operation is reached, then we need to do the real evaluations. Previously, I introduced that in Spark, the fault tolerance is achieved by re-execution using the lineage concept. So we have a lineage graph in RDD. RDDs will keep track of the lineage for the data to represent how the data in this RDD is achieved. And RDD will have enough information about how it was derived from to compute the partitions from data in stable storage. For example, RDD1 is lines, and RDD2 is errors, and RDD3 is HDFS errors. So the lines starting with errors and also contains the HDFS word. And finally, map underscore split tab character 3 is to split the line according to this tab character and get the third element. And this, which is a time field, is also RDD. So we have 4 RDDs. And each RDD will keep track of the lineage that's used to generate the data stored in it. So for example, in RD1, it's just lines. For RD2, it's from lines to errors. In RD3, the lineage is from lines to errors to HDFS errors. So as a result, if some data is lost in this RDD, and it will check the lineage stored in this, and note that, okay, so in order to recover data, we need to get the data from lines to errors and to HDFS errors. So it will do all the executions according to the lineage graph. And so that's how the fault tolerance is achieved in Spark. And the partitions can be recomputed in parallel on different nodes, so without having to roll back to the whole program. So it's computed in parallel. And now let's deconstruct the operations. So remember that we have RDD, transformation operations, and action operations. And transformation operations will transform one RDD to a new RDD. And the action operations will take the RDD as a parameter and then do some operations then to generate the values out of Spark. So we are able to see the values according to the action operations. So now look at these lines of operations, okay? So first, we have a base RDD, so this is RDD. And we create this RDD according to this text file operation to read the data from disk in HDFS to memory. And next is lines filter. This is a transform operation. So filter will only keep the lines starting with this error word and to create errors RDD, errors. And this is a transformation. So from lines RDD, transformation, and to errors. Okay, from lines to errors. And errors persist will cause the errors RDD to be cached in memory for further operations to different tasks. Okay, next is errors count Now count is an action operation, so it's an action operation, which means that this errors RDD will be processed to generate a value. So count will count the number of lines in this errors RDD. And it causes Spark to first read data from disk. This corresponds to this line. And next will filter the result, filter the lines not satisfying the condition. And next to for different partitions will process in parallel to get the line to get the number of lines in each partition, and then to combine the sums in the driver to get the final count in the errors RD operation. And we can also put the transformation and action operations together. So for example, we can use errors.filter this condition. This will generate a new RDD, and then we use map. This is a underscore dot split. And map is also a transformation operation, so this is also a new RDD. And finally, collect. And collect is action operation, so it will convert the data in the RDD to a list, a collection of values. Then these values can be read from by us. We can write everything together in one line, but the evaluation will only be performed when we reach the action operation to this collect function. So when we get when Spark reaches the collect function, and all the previous operations will be executed in order to get the result for this action operation. Okay, this is just one very simple example to show that how Spark can be used to solve some problems. And Spark context, this is application entry point for the program to interact with the Spark platform. So in your program, you always need to first create the Spark context object. And in the Spark shell, this object is already created for you, so you don't need to do anything for that. But in your program, you always need to create it first. And once a Spark context is created for you, then you can use this object to create RDDs and to create some other useful variables, and also to access Spark services and run jobs. Spark context is essentially a client of Spark's execution environment and acts as a master of your Spark application. It's kind of a master of your Spark program. And the first thing our Spark program always need to create is Spark context object. And when you create this Spark context object, you need to tell Spark how to access a cluster. So which type of cluster manager you want to use. Your own, Masters, or your Spark's own cluster manager, or local thread, so different type of cluster managers, and also other configurations you need to give for this Spark context object when you define it. It's like the job configuration in MapReduce. And in Spark shell, it is already created for you. Okay, and in RDD, remember that you can persist or cache the data in memory. So this is one of the most important capabilities in Spark. And because if you can cache data in memory, then if you have enough memory, so it means that later the data processing can be based on memory operations, which is much, much more efficient. And when you persist an RDD, so each node stores any partitions of it. So you can reuse the partitions in the other actions on that data set. So each persist RDD can be stored using different storage level. Memory only, so means that you can only use memory to store RDDs. And so you will store RDD as deserialized Java objects in the JVM. But it's possible that RDD does not fit in memory, right? Because data may be too large. So some partitions will not be cached and will be recomputed when they are needed. So see here, because you said memory only, so if your partitions, not all your partitions can be cached, these partitions will not be written to disks, okay? They will be just discarded, and these partitions, when they are needed, they will be recomputed. So that's the difference. This is the default level. But you can also use memory and disk. And in this case, if the RDD does not fit in memory, then some partitions, if they cannot fit into disk, and okay, they can be written to disk. And sorry, if all the partitions cannot fit in memory, some partitions can be written to disk. And later, when they're needed, you can read them from disk. So that's memory and disk. So the different storage level. But in any case, it means that you persist the data in the storage. Okay. Cache is just the persist storage level memory only. So you can use both cache function and persist function to cache the data in storage. And why we need to cache the RDDs? So let's look at the example again. Okay. So without persist, and then count is an operation. So count will do the operations on this errors RDD. And now this errors RDD, after this count operation, errors RDD will be discarded in memory. It will not be stored in memory after this count operation. Okay. So if you, after this count, if you do another errors.count, which means that the file need to be loaded again and computed again. So all the operations here and here need to be executed again because after this action operation, the RDDs are not kept in memory. So if you do another action operation, then all the evaluations need to be performed again. So that's why you need to persist the RDDs if it is necessary. So persist will tell Spark to cache data in memory to reduce data loading cost for the other actions on the same data. Errors count and another, in the example, so first we do errors count, this one action operation, right? And after we read the number of lines in the errors RDD, and without this line, the errors will be discarded. But with this persist, we know that errors will be persist in memory. So next errors filter, map, collect. So this is another action operation on this errors RDD. So this operation will now go directly to the memory to get the errors RDD, instead of to reading the data from disk to memory to create RDD and then do this transformation and then to get the errors RDD. So that's a difference. Okay, so that's why persisting RDD is useful in some cases. And this is also a transformation operation. If you call persist in your Spark program, actually it also does nothing because of the lazy evaluation. It just means that, okay, Spark knows that according to this, this line, Spark knows that you want to persist this RDD. Okay, and then when the action operation is reached, so Spark will do all the computations and then persist this RDD according to your program. Okay. The next topic is one important type of the RDDs in Spark called key value RDDs. So in MapReduce, the data types are based on key value pairs, right? So in the map function, you need to read a list of key value pairs, and in the reduce function, you also need to read a list of key value pairs and also generate a list of key value pairs as a final output as well. And for Spark, so they also support the key value data type to do the similar tasks. So that's why the key value RDDs are designed within the RDD to deal with similar applications in MapReduce. And each element of a pair RDD is a pair tuple with a key and value. And some key value transformation functions include reduce by key, sort by key, group by key. So reduce by key will return a new RDD of data type K and V. It's a list of key value pairs where the values for each key are aggregated according to the given reduced function. For example, you can do reduce by key, you give a sum function to this function. And then for all the key value pairs with the same key, the values will be summed together. And finally, the RDD will store a list of key value pairs with the key and the summed values. So that's for reduce by key. And for group by key, instead of doing the sum, it will just group all the values together as a iterable V type, as a collection of all the values in the new RDD. There's also a key value pairs list, but the value is a group of values instead of just one value in the reduce by key function. And sort by key, so we'll sort the key value pairs based on the keys in ascending order. So that's a sort by key. These functions are similar to some operations in MapReduce. Remember that in MapReduce, what you do, the map function will take the key value pairs as input, right? And then the result, intermediate result, are also key value pairs. So in between map and reduce functions, there's a shuffle and sort phase. The shuffle and sort phase is kind of a group by key, actually. They will group the values for the same key, right? And then the key and the group, a list of values, will be sent to the reduce function for processing. So you can view this group by key as kind of the procedures as in MapReduce in the map phase. You do some kind of processing, and then you group the results according to the keys as the intermediate results. And later, based on the group by key results, you can do some reduce, you can do some aggregation functions, and that will be the action operations part in Spark. So for the action operations. Okay, so let's look at some examples on pair RDD to see if you can get the results for them. So the first one, we create our pair RDD from existing RDDs. We have a list of key value pairs. The key is a string, and value are integers. So we have this list, and then we use this parallelize function to create them, to transform them to RDDs. And if we use collect for each print, so what we will get just get the result like this. We will get a list of this. So you can see what will be the output like when you do the labs. Now let's look at some more complex examples. Reduce by key function. The reduce by key function will reduce key value pairs by key using the given function. So for example, pair 1 is pairs reduced by key xy to x plus y. And then pairs 1 collect for each print line. So what will be the output for this piece of code? I know you're not familiar with Spark and Scala now, but you can still make a guess, right? This should not be very difficult according to this RDD. Reduce by key, you first need to understand what does reduce by key mean. Reduce by key will first process the key value pairs according to the keys, then reduce the values according to the same key and based on the given operation, right? And then also create new RDDs. Just reduce by key is just a transformation operation. It's not an action operation. So, yeah, that's correct. That's correct. So because for the RDD pair 1, it contains 4 key value pairs, right? And that reduced by key. For the key value pairs with the same key, it will apply the reduce function here, given here. So only is they have the same key, right? And then their values will be obtained, then apply the function given here to the values. It's a sum function. So all the values associated with the same key is will be summed together. We'll get 6. So the result will be 3 key value pairs, which is this 2 is 6 and spark 5. So that's for this part. Okay, yeah, it should be not very difficult. Map values. This is also a very important and also widely used transformation operations. And map values is work on values only, which means that given a key value pair, and this map values function will only apply the function you're given to this map values. Apply this function to the values part, not to the key part. Okay, so you can guess what will be the output for this piece of code. Pairs map values x to x minus 1. Yeah, that's correct. So that's also very obvious, right? So after I explain the map values, you should be able to know what will this piece of code do. So first, pairs, all the 4 key value pairs will apply this map values function. And because the given function is x minus 1, so all the values will be processed by this function. So it's 1, 2, 4, 2. So that's the result. And group by key is to group the key value pairs according to the key. So if we use pairs group by key collect, then, well, it's obvious. Only these 2 will be grouped together. And the result will be these 2 A's and 3 and 3. So it's just a group of values. And nothing will be done to the group of values, but just list them there and spark 5. So that's group by key. These are very simple operations of pair RDDs. And so in the exam, actually, there are some similar questions like this. Okay, what's the question?
Would the reduce by key function? Would it sort the keys?
You mean group by key or
Reduce by key?
reduce by key? No, they will not sort the key. So reduce by key, first it's based on by key. Okay, all the key value pairs will be first, you can think a group together. Not suitable to say group. So all the key value pairs will be processed together. Okay, for example, A3, A3, the 2, they have the same key. So which means that they will be processed together. Now how to process is based on the function you gave. So reduce by key, and the function you give here is to do the sum, to sum the values for the same key. So no, it's not similar to the reduce function in Hadoop MapReduce. I have said, yeah, it is similar, right?
Seems like combine.
Also not combiner. Combiner is just a local aggregation. So this is a kind of reduce. Yeah, you are right. It's similar to the reduce function in MapReduce. So, but so the function is actually, yeah, they are similar, because in MapReduce, what you do is you receive one key and a list of values, right? And you do the aggregations for the list of values. Here, you also have the similar results. So for all the values associated with the same key, and you will apply the functions you're given here to these values. Yeah. You can think about this part is a reduce function, right?
In Hadoop, we receive the keys in order.
Yeah, you receive the keys in order, but here you don't have the orders. You do not have the orders. It's based on the partitions. Okay, you know, this data will be actually they have different partitions. That partition that's split into different parts. So actually, A3 and this3, it's possible that they are in different partitions, right? And then reduced by key first will be applied to different partitions. And the different partitions will get some results, right, for the same key. Assume that it's in one partition and it's on another partition. And then for different partitions, it gets some results, and the master of the Spark program will get a final result for different partitions to return the to get the results. And okay, so this is just some very simple examples of the usage of these applications and of these functions. In the exam, to talk about the exam, in the exam you will be given some more complicated codes, and you need to write output. That will check your understandings of these actions, operations, and transformation operations. Okay. Okay. So that's for. Next is about the partitions. So as a pair RD operations take an optional second parameter for number of tasks. Okay, so 5, and it means that the results will be partitioned according to the given parameter, how many partitions you will get in this RDD. Okay, so that's about the pair RDD and some examples. So the next part is about the Spark program model. What I will do in this part is to use word count example to show you how Spark works. Okay, hopefully this word count example can help you to help you understand the more details of the Spark program, Spark platform, and similar to the MapReduce, and word count in Spark also does the same thing. So given a huge number of documents or a huge document, and you are going to count the frequency of the terms in this document. And okay, so I will give you the codes in Spark to do word count. You can see it's just the 1, 2, 3 lines. That's it. So very simple, right? Compared to MapReduce. In MapReduce, if you want to do word count, you need to write very complicated Java code. But in Spark Scala, it's very, very simple. But if you use Java, it's also not that easy. If you write Java programs, you also need to write write more codes for word count. And what we can understand at this stage is that we know that first we read the data from a test file, right, from HDFS. And so the last one seems that we are saving the result to HDFS as well. Okay, so that's what we can understand. So in between this line is the most important part. File is a RDD, it's a lines of of strings, right? And then first flat map and line to split. Okay, so here it seems to split the lines according to the space character. And then map again word to word 1 and reduce by key. Okay, so we have some part which is not very straightforward to us, right? First, what is flat map? And next, about map, why we map this, and then reduce by key, how reduce by key is performed. So let's look at details, one operation by operation. So in Spark, user application creates RDDs and transform them and run actions. And this results in a directed cyclic graph of operators. So the Spark will do some optimizations for this DAG to get a correct order of execution to get the best performance. So DAG will be compiled into stages, and then each stage it will be executed as a series of tasks, and one task for each partition. And in word count in this example, so let's look at what we will do. Assume that we have partitioned this RDD into 4 parts. And the first line will create one RDD of type string. We read this the file from HDFS and start in a file RDD. And remember that it's just a transformation operation. Okay, it's because it's laser evaluation, nothing happens here. And next words is from file flat map line to line split. It's also RDD. In this line, actually what it does, it will split the lines into words according to the space character. Okay. Now the lines will be splitted into a list of string, a list of words. And so the RDD data type will be list string. Now, the original documents becomes a list of words. Okay, so that's the second line. But remember that the partition is 4, so it is also have 4 partitions in the RDD. And pairs is equal to words map T to a pair of T and 1. So this is just similar to the MapReduce function, right? In MapReduce, you also convert one term to a key, the term itself, and a value 1. That's it. And now the RD is transformed to a pair of RD, a pair value, string and integer. And next is count. So at this stage, all are transformation operations. But now we have reduce by key. This is also a transformation operation, but we need to do some exchange because of the reduce by key operation needs to do the reduce function according to this function, according to the given function for the same keys. But the result for the same key may in different partitions, right? So there across different partitions, there may be require some data exchange from different partitions. And so this part is similar to the MapReduce reduce function. Just do sum for all the ones, or value ones for the same term, T. Okay. And finally, is collect. This is action operation. Okay, so at this stage, now all the operations will be executed in Spark. So first read the file from disk, then do flat map, then do map, then do reduce by key, and finally do collect. So this RDD will be collected as an array of pairs. So this the detailed procedure in Spark. And as introduced before, so this transformation operations and action operations will be represented by a DAG, and DAG will be compiled into stages. And in this example, there will be 2 stages. One is the stage 1 include text file, flat map, and map, and stage 2 is reduced by key and collect. And the scheduler will examine the RDD's lineage graph to build this DAG, and stages are just a sequence of RDDs. And in each stage, there's no shuffle in between. And across different stages, there will be shuffle across different partitions. So the boundaries across different stages are the shuffle stages. So this is very similar to MapReduce, right? So it's just like the map stage, like the reduce stage, and in between the shuffle, but there's no sort here. So represented by stages, so that's stage 1, stage 2, and then in between is a shuffle stage. And so Spark will first read HDFS split and then apply both the flat map and the map operations, and start the partial reduce, and then write the shuffle data. And that's in the stage 1. And in stage 2, it will read the shuffle data and do the final reduce and send the results to the driver program to get the collect. Remember that everything happens in memory, so that's a major difference with Hadoop MapReduce, because in MapReduce, from here to here, is you need to use the disk for data sharing. So the data need to be written to disk, and then here you need to read the data from disk. But here there's no disk involved, there's no I/O cost involved. So that's why it's more efficient. For the stage execution, so each partition will get one task to process this partition. One stage will create a task for each partition in this new RDD, and also Spark will serialize the tasks, schedule and ship tasks to the slaves, to the workers. And all this will happen internally, so we don't need to know how it will be executed. So this the low-level details hidden from us by Spark. And in Spark as a whole, the word count is like this. So the transformation operations are this part. Then finally is the action operation. And actually this part is just similar to MapReduce. So the lines will be split according to the space character to words, and each word will be mapped to the word itself and the value 1. And next, reduced by key will perform the aggregation according to the keys, and finally to collect or save as a text file will read the data stored in RDD to a real value out of Spark. So that's a basic structure. But we can see that the code is much more concise in Spark, right? One thing has not been explained is that what difference between flat map and map, right? There are two map functions. While here we use flat map, and here we use map, right? The difference is that, so remember that what does file stores? File stores lines of strings, right? So in this RDD, there are many lines in this RDD, and each line is a string. And a flat map will first split each line to a list of strings, which is a list of terms. And so now each line becomes a list. And a flat map will merge all the lists to a single list. Okay, so that's a flat map. But if you use map, then you will just map each line, each string to a list of strings. Then what you get is an array. It's kind of an array of a list of strings, not a single list. So that's the difference between flat map and map. So we can see this example. Assume we have two files, one short sentence, another short sentence. Okay, and we have this text file. We read this file from HDFS. So we get an RDD. It's a string of type, that type string. Now, if we use map, and then we collect what we will get, we can get with an array of array. Okay, it's not a single array. It is an array of strings. If you use map function, because originally in this RDD it is several lines of strings, and now if you apply map, so each line will become one array. And then the final result will be an array of string arrays. But for flat map, it's similar to map, but each input item can be mapped to, they will be merged together. So if we apply a flat map, then these arrays will be, or these lists will be merged to a single list or a single array like this. So see the difference between map, flat map, okay. So that's why here we need to flat map. We need to make sure that what we get at this stage is just a single list of terms. And then for this single list of terms, we apply map to transform each term to the term and 1. And finally, we do reduce by key to get a count for the terms in this file, okay. So that's the difference between a flat map and map. There are many RDD operations, such as map, filter, flat map. That's what we have used now, and group reduced by key and the map values and these operations. This data type you need to follow for this function. F you're given to this function, to these transformation operations. And our action operations, we have used reduce and count, collect. You can see that all the RDDs are transformed to a value of some type, such as long or a sequence or some data type. And when you, this is a very useful link for you to use when you do Spark programming. If you are not familiar which function to use or how to use a function, you can click this link, and they give you many useful examples. For example, group by key. So you can see this is group by key, right? It will tell you how to use group by key and what does group by key mean. And then it will give you an example about what will be the result after applying a group by key. So this link is very useful for you to use for Spark programming. Okay. And there are some other concepts such local variables. Let me check the time. Okay, I'll quickly go through these slides. But using local variables. So in Spark, so any external variables you use in Closure will automatically be shipped to the cluster. So for example, query is we get some results read from the STD input, standard input, and then we use pages filter. Use this function to check which page contains these query terms. And then we count numbers. And query is a external variable you use in the Closure, right? So this will automatically be sent to the cluster, to send to each node for processing this function, because query is an external variable of this Closure. So each task will get a new copy for this local variable, right? The variable must be serializable. But it means that this local variable can't be too large. Otherwise, we'll need to send a large data structure to many nodes in the cluster, right? So that's why in Spark, you need to have a way to share variables to avoid this. So when you perform transformation and actions that use functions, so Spark will automatically push a Closure containing that function to the workers, so it can run at the workers, right? But any variable or data within a Closure or data structure will be distributed to the worker nodes along with the Closure. As in example, the query is this external variable to this Closure. So both the Closure and this environment variable will be sent to the worker. And so when a function is executed on a cluster node, it works on separate copies of all the variables used in it. If this variable is small, like this, it is just a line of string, it's okay. But sometimes these variables may be very large, and these variables then can't be shared across workers efficiently. So in this case, we need some new ways to do the data sharing.